For 60 years, we have been throwing giant, expensive firecrackers into the sky to deliver satellites. A rocket is roughly 90% fuel by weight. That ratio has barely changed since the 1960s. Getting 1 kilogram of cargo to orbit currently costs between $1,500 and $2,500. Getting it to geostationary orbit costs significantly more. Per kilogram. Every single launch. There is a theoretical alternative that reduces that cost to approximately $10 per kilogram. Not 10% cheaper. 99% cheaper. It is called a space elevator, and the race to build it has already begun. The concept is simple. Anchor a cable to the equator. Extend it 36,000 kilometers to a counterweight at geostationary orbit, where a satellite orbits at exactly the same speed Earth rotates. The cable stays taut. Vehicles climb it. No fuel required. The physics has been mathematically validated since 1895. The problem has never been the physics. The problem is always the same thing. The cable. Specifically, what material could possibly be strong enough? Steel fails immediately. The cable must support its own weight across 36,000 kilometers. Steel snaps long before reaching the required length. Every conventional material fails the same calculation. The numbers are not close. The theoretical solution is carbon nanotubes, cylindrical carbon atom structures roughly 1 nanometer in diameter, approximately 100 times stronger than steel at 1/6 the weight. On paper, they work perfectly. The practical problem is manufacturing. The longest carbon nanotube ever produced in a laboratory measures a few centimeters. We need 36,000 kilometers of structurally perfect cable. That gap is not a gap. It is a chasm. Graphene is another candidate. Same carbon lattice, flat sheet form. Both materials have been theoretically sufficient for decades. The challenge is manufacturing them at scale, without defects, consistently, economically. China currently leads global research output in carbon nanotube manufacturing. The US, Japan, and South Korea are competitive but behind at industrial scale. Whoever solves manufacturing first does not just win a Nobel Prize. They win the space economy. Here is the geopolitical twist nobody in mainstream space coverage discusses seriously. A space elevator must be anchored on or very near the equator. The physics requires it. And the equator does not run through the US, Russia, China, Japan, or Europe. The equator runs through Ecuador, Colombia, Brazil, Kenya, Somalia, Indonesia, and several Pacific Island nations. Countries never considered major space players. That calculation is about to change completely. Think about what the Suez Canal did for Egypt. A geographic accident became one of the most leveraged pieces of real estate on Earth. The equatorial position for a space elevator is identical logic, multiplied by the entire solar system. The hosting nation would control landing rights, transit fees, and security over what goes up and what comes down. The legal framework for this does not exist yet. That absence is itself a geopolitical opportunity for whoever moves first to define it. Japan's Obayashi Corporation published a space elevator construction plan in 2012 with a target completion date of 2050. They were not dismissed as science fiction. The material science trajectory, while challenging, is not implausible over a 30-year timeline. China has been less publicly specific, but significantly more active. Chinese researchers have published extensively on nanotube manufacturing at scale. China's space program has consistently achieved announced goals ahead of schedule. The US military's interest is the least discussed and arguably most consequential. A space elevator allows rapid, low-cost deployment of military assets to orbit. Satellites, surveillance platforms, weapon systems, all dramatically cheaper. The Pentagon has studied this quietly. The commercial rocket industry, SpaceX, Blue Origin Rocket Lab has invested billions in cheaper rockets. A functioning elevator makes their entire business model obsolete overnight. That industry has structural incentives to delay elevator development. That incentive is not hypothetical. Now, for the part space elevator, enthusiasts tend to move past quickly. What happens if the cable breaks? We are talking about 36,000 kilometers of ultra-high tension cable suddenly released. The physics is not subtle. The lower portion falls toward Earth, not straight down, in a complex whipping arc influenced by Earth's rotation and atmospheric drag. The impact pattern would be continental in scale. This is a civilization-scale engineering risk. Space debris is equally serious. The cable passes through low Earth orbit where thousands of debris fragments travel at 28,000 kilometers per hour. One significant collision could trigger catastrophic cable failure. The debris problem must be solved before the elevator problem can be. Military vulnerability is equally uncomfortable. A 36,000 kilometer cable is the largest target in human history. Any nation with anti-satellite capability could threaten it. No current military doctrine addresses defending 36,000 vertical kilometers of critical infrastructure. Set the risks aside and consider what a functioning elevator actually enables. At $10 per kilogram to orbit, space mining becomes immediately profitable. The asteroid belt contains enough metals to supply Earth's industrial needs for millions of years. Water ice on the moon becomes viable as rocket propellant for deeper missions, once equipment reaches orbit cheaply enough to mine and process it. The elevator does not just change Earth-to-orbit economics. It changes the economics of the entire inner solar system. Orbital hotels, manufacturing facilities, and solar power satellites, all economically marginal at current launch costs, become commercially viable at elevator economics. The space economy, currently worth roughly $500 billion annually, expands by orders of magnitude. The entity controlling the elevator controls the choke point to everything above Earth's atmosphere. Every satellite launch, every orbital mission, every space mining operation. The toll booth analogy is not metaphorical. It is literally accurate. The first nation to build a functioning elevator does not just gain a transportation advantage, it ends the rocket age. Every competitor's existing space infrastructure becomes strategically obsolete overnight. That is not an incremental advantage. That is a civilizational discontinuity. The legal frameworks governing space elevator development have not been written yet. That is not a problem waiting for lawyers. That is an opportunity waiting for whoever moves first to define the terms before everyone else arrives at the table. The material science is advancing. The geopolitical competition is intensifying. The economic incentives are enormous. The space elevator is not science fiction. It is an engineering problem with a known solution, waiting for one material science breakthrough to unlock. That breakthrough could come from a laboratory in Tokyo, Shanghai, Houston, or Nairobi. When it does, the race to the equator begins immediately. And who owns the sky gets answered very quickly by whoever moves fastest when the starting gun fires. If you were the leader of an equatorial nation right now, Ecuador, Indonesia, Kenya, and a superpower approached you with an offer to build a space elevator on your territory, what would your terms be? Drop your answer in the comments. Subscribe to GeoMind Studio, because this story will not wait.